I would now like to introduce Margot Mansfield. She is a climate change and coastal hazards analyst with the Massachusetts Executive Office of Energy and Environmental Affairs, or EEA, and the Office of Coastal Zone Management, or CZM. She supports implementation of EEA's Municipal Vulnerability Preparedness Program and leads their work on integrating statewide climate change projections into the MVP program and the Massachusetts Climate Change Clearinghouse. She also supports CZM's Storm Smart Coast program, including development and review of coastal hazards data sets and efforts on developing a regional monitoring protocol and guidance for living shoreline projects in coastal New England. Margot holds a Master of Science in Earth Science from the University of Maine and a Bachelor of Science in Earth and Space Science from the University of Washington. And we also welcome Julia Neisel, also of the Office of Coastal Zone Management, where she is the Coastal Shorelines and Floodplain Manager. And Julia will actually be introducing the project. Okay. So Julia, Margot, the floor is yours.
Thank you for inviting us to be part of this webinar series. So my name is Julia Neisel, and I manage the Shoreline and Floodplain team here in Massachusetts. And I'm happy to see that there's a number of Massachusetts partners on the webinar today, and also a bunch of other partners largely across the East Coast, but also from some other internal sections of the country, so that's exciting. So back in 2015, our State Department of Environmental Protection invited us to partner up on this project to get a better handle on how much of our elevated coastline we're losing over time to erosion. And while Massachusetts has been very progressive in terms of looking at shoreline change over the years, that shoreline change assessment has largely been focused on the mean high water shoreline. And we are excited to work with DEP on looking at the loss of our elevated coastal bank landforms and think about how that plays into how we regulate coastal resource areas and look at floodplains and performance standards that are tied to those. So when we kicked off this project with DEP, we knew that we wanted to take advantage of our existing shoreline change information, but also utilize the latest LIDAR data that was available across our coast. And we typically look at about 1,500 miles of shoreline when we do these coastal hazards assessments and these vulnerability assessments. And we actually had very good LIDAR coverage over the last couple of decades across that area. So we were very fortunate that we could do a remote sensing application for this project. And Margot is going to be able to dig into the methodology that we employed for this project and talk about some of the applications that we're considering moving forward with our partnership with DEP. I'm sure that you guys can all appreciate this need to think about coastal vulnerability out of the traditional FEMA coastal flood zones. And I'm looking forward to the discussion at the end of the presentation to potentially hear about what you're all working on. So now I'm going to turn it over to Margot, and she's going to get into the details.
Thanks, Julia. So given that our audience today is listening from a wide geographic region, before I dig into that methodology and the results, I just wanted to share the working definition of what we mean by coastal banks. It is a regulatory term defined in the Massachusetts Wetlands Protection Act, and is used by MassDEP to mean the seaward face or side of any elevated landform other than a coastal dune. And I'll touch on this being a remote project. There's some challenges in making that call. But essentially looking at these landforms that are at the landward edge of a coastal beach or land subject to tidal action or another wetland. DEP's wetland delineations was a primary data source for this project, and it covers a wide range of coastal bank types, from hard glacial rocky ledges to more unconsolidated till bluffs. And I'll share some examples of this range in Massachusetts in a moment. So this project was broken up into two phases. The first phase was to identify and delineate the current top and toe of coastal banks in Massachusetts. And to accomplish this task, I used the most current, readily accessible, high-resolution elevation data, or the LIDAR data set. And so for this project, current refers to the 2013-2014 ground conditions. The geographic scope of this project was limited to the predominantly ocean-facing shorelines in Massachusetts, similar to CZM shoreline change data set that Julia mentioned. I used a semi-automated methodology to delineate the top and toe of coastal bank, which I will address a bit more detail momentarily. So after establishing the top of coastal bank, I measured the short-term change in position between my oldest data set from the early 1990s and that 2013-2014 LIDAR data set. Unlike CZM's shoreline change data, these landforms only have the potential to move in one direction, that is landward. The measured change in position then is the amount of erosion that occurred over this 24-year window between 1990 and 2014. The second phase of the project was to apply this same automated methodology at multiple time steps for additional LIDAR data sets to help increase our confidence in capturing the magnitude of erosion and episodic nature of these processes. Because the natural function of coastal banks and episodic and potential irregular nature in which they erode, the hazard is presented as a total loss or erosion landward as opposed to a rate. And this is one of the key differences from shoreline change data sets you might be familiar with. I mentioned earlier that this was a coastwide desktop study, and it was limited to those predominantly ocean-facing shorelines in Massachusetts, which roughly corresponds with the same footprint as the CZM shoreline change project. The gray shading here are the 78 coastal communities in Massachusetts. The orange line on the map shows the extent of coastal bank identified for this analysis, and the images here are some examples of the range of coastal bank types in Massachusetts, including, but not limited to, low relief and rocky ledge types that we see in the North Shore. So examples here from Rockport and Marblehead, to more sandy and unconsolidated till high bluffs down on the South Shore in Plymouth, Situate, and also out on Cape Cod, Truro, and the islands and Nantucket. The next series of slides detail the various data sources that I used for this project, and starting with the imagery sets that were used for some additional photo interpretation to determine the presence of coastal bank. Both aerial imagery and oblique imagery were examined in this step to provide opportunity to capture features that were omitted from the original 1990s wetlands delineation data set. While the primary target of the project was to capture coastal banks, in cases of ambiguity distinguishing coastal dune from coastal bank, both in reviewing the current boundary delineations from the MassDEP Wetlands data set, but also from additional photo interpretation, the feature in question was included in this analysis in the study area as long as it appeared to laterally transition from coastal bank to dune. If the feature was clearly a dune or a dune field, it was not captured for further analysis. So through this, this initial step, I captured an additional 83 miles of coastal bank and mapped those within the defined spatial extent. The oldest mapped bank positions for this project were pulled from those MassDEP Wetlands 1 to 12,000 data sets, which utilize unregistered aerial photos spanning from 1990 to 1993 with a horizontal uncertainty of 34 feet. To compare the position of coastal bank using the oldest data set, I extracted all the bank polygons labeled BA, shown here in the brown polygon and these circles here. And then I further extracted the landward delineation representing the top of this feature for this time step. So ranging from 1990 to 1993 based on the original individual aerial photos. This older data set with the 34 feet of horizontal uncertainty is the greatest source of error in this project, but we felt that the outcome still delivered a macro view of erosion trends. And we did collaborate with one of the original authors of the wetlands data set to decide that it was warranted conducting this additional photo interpretation. To map the most current top of coastal bank, I used high-resolution elevation data, or the LIDAR, light detection and ranging data, from the 2013-2014 time range. This was the most current data set at the outset of this project. The horizontal uncertainty with this data set is approximately 1.5 feet. And then the images shown here are the spatial extent of the full data set, so on this far left, smaller box, a zoomed in region of the outer Cape Cod, and then two display options for visualizing the relative difference in height. So for this middle image here, the brown denotes higher elevations and green lower elevations. And on the far right, the warmer colors, the reds and oranges and yellows, have a higher elevation than the cooler blues. So to accommodate for a quicker processing time and for the auto-delineation, I clipped the LIDAR data, which is why you're just seeing a thinner band here in the far right image. For the phase 2 portion of the project, to map additional bank positions between the early 90s and 2014, I used a series of additional LIDAR data sets that were available. And for ease of computing and visualizing, I grouped those data sets that were close temporal snapshots. So for example, here, I have a fairly comprehensive set from 2000, with the exception of the Boston Harbor region, which I complemented with the 2002 data set. Similarly, grouped data sets from 2005 and 2006, and from 2010 to 2009 to 2010. Go back real quick, just to say that the 2013-2014 data set is the most comprehensive in terms of spatial coverage, but these other sets provided valuable intermediate time steps. And so in addition to visualizing and symbolizing the elevation, I worked with a tool, an ArcMap, that allowed me to review the profile across the landform, so perpendicular, to view the relief, and I'll show you what that looks like in a moment. Unlike traditional methods of hand or manual digitizing, the method I use to delineate the top of banks utilizes this high-resolution elevation data set, the LIDAR, in combination with an ArcGIS approach that essentially auto-delineates the top of bank. So to run this tool, I input the desired stretch of LIDAR, so this color band strip here. Again, the red and orange are the higher elevations and the blue are lower elevations. And then having to select two endpoints, these little green dots down here, so that the tool then does a least cost analysis on the LIDAR data between the two endpoints, which is essentially just a function of distance, slope, and profile curvature. So what I mean by profile curvature, there are three main types, either convex, concave, or planar. And with the tool, it doesn't really matter what the morphology looks like. It's trying to pick out that point of highest inflection. And so in ArcMap, there's a tool where I can draw a profile perpendicular to my landform. You can see in the graph here above that where this red arrow is pointing to, I can, in ArcMap, click on that. It'll show up on the delineated output where that is to sort of check reasonable outputs from the auto-delineation. And so just to bring us back to this image, the white line here is, for this stretch of shoreline of coastal bank, is picking out the top of coastal bank based on that greatest point of inflection. So these are a few quick examples of what that auto-delineation output look like for the top of coastal bank in orange, and for the toe of the coastal bank, or the base of the landform, in this pinky peach line. I should say I was able to make a small tweak in the tool to look for the inverse of that highest point of inflection to be able to pull out the toe of the landform. And this was more of a proof of concept, so I won't be touching too much more on the toe of these landforms. A few more examples of the tool output, and just showing differences in the level of vegetation, the slope of the faces, height of bank, and orientation. So this image here is explaining how we measured the top of coastal bank. So the image shows multiple time steps of bank positions from the oldest data set in the purple, that's from the 1990s DEP wetlands delineation, to the most recent data set in pink, which is the 2013 or 2014 LIDAR-derived delineations. And then the blue, green, and yellow lines there are positions from this outputs from the same auto-delineation methodology on the additional LIDAR data set. But to measure the change in position of the top of coastal bank, we only use the 1990s and the 2013, 2014 data set to calculate the distance marked here by the black dots, or magnitude of erosion over this 24-year time span. And that is that distance is labeled on these transects here. So in this case here, we're looking at a range of over 70 to 100 feet of movement in the landward direction. So I did want to, that was the sort of heavy technical lift of the presentation. Before I start sharing some more examples and what the web map viewer product looks like, I did want to pause to see if there were any questions that folks had. I didn't see anything in the chat, but I don't know, Audra, if you've seen any on your end.
Yes, Margot, I did have one question sent to me. What is the name of the tool that you use to delineate the bluff, crest, and toe?
It was a tool that we built ourselves using the model builder. So it was, but primarily it's least cost tool within the ARC toolbox.
And another question, can this analysis work with forested shorelines?
Forested shorelines. Well, it's going to be based on the level of accuracy from your LIDAR. That was the primary data input for the analysis.
So as long as the bare earth assessment is accurate.
Yeah. I did see a few more questions in the chat that I can respond to. In terms of ground truthing, no, this was a desktop analysis. You know, we have some knowledge of certain areas based on sort of projects that we've gone out to scope, but there was no sort of ground truthing, official ground truthing component to this project. And in terms of the minimum height of bank analyzed, pretty low in some cases. Try to have the cutoff around 3 feet. So you can argue whether that's really a bank, but if it's functioning as a bank, then and it was determined from the photo interpretation, sort of presence absence, then it was included to the best of my abilities. Okay, looks like that was the majority of the questions at this point. If you have more, please feel free to ask at the end.
Margo, I have one more question that just came in. If you don't mind, we'll just go ahead and take it now. Did they compare change rates from this time period to longer time periods, or was there a trend of increasing change?
So we didn't compute change rate. We felt like that was a misleading way of characterizing the function of these, unlike shoreline change rates, where you'd have sort of multi-directional ability of those landforms. So at this point in time, we didn't compare it to any other time frame, as this was what we had available at the highest resolution. So I know that there are aerial photos that predate 2000, but for the scope of this project, that would be a different type of methodology than we were able to employ for this auto-delineation approach. Okay. So I do want to pivot now into the online map viewer. So we used ArcGIS Online. I included the link there at the bottom. Right now, this is the only place where it lives. We have some internal conversations still to figure out how it would best link up with some of the other data sets that we'd mentioned and other platforms that the state offers. But for now, it's on this ArcGIS map viewer. You can find some of the background information on the project. I'm just showing screenshots for today. So what you have in the black box here is the list of different layers, and each of those are hyperlinked, takes you to their own information page, providing the metadata for that layer. And then the biggest, in addition to the linear position itself, there's also those transects with the total net position movement measured in feet, and that's what this NPM sort of arrow is calling your attention to. When you click on the transect, it'll spit out this box of attributes with different values. So in addition to what that distance of erosion was, it also tells you what the oldest and newest data types and years were. So for the oldest, in most cases, it's going to be that 1990 aerial photo that was used for the DEP wetland data set, and except for those cases where I added to the project, added to the presence absence. In that case, you'd be comparing LIDAR to LIDAR. And then being able to note what the the number of years over which the distance was calculated. So for the most part, it's over 24 years roughly, but in some cases it's less than that, depending on whether that older 1990 data set was present for that particular coastal bank. So when you launch the map, what you'll see is it'll default take you to the full extent of the project. So here is Massachusetts, or the coastal Massachusetts, I should say. And on the top here in the orange box, there's these three little icons. The middle one here is for the content, so that's what's displayed right here. At the top is the coastal bank transects, and as I said, if you click on those, that's where you'll get the readout of the attribute table, but it's also labeled the transects themselves once you zoom into a certain extent. Then next is the top of the current coastal bank. So again, this is the 2013 or 2014 LIDAR-derived delineation. And these are all grayed out at the moment just because of the zoom extent, but as you get in closer, those will pop up. And these, and highlighted here by this orange bar are the additional LIDAR-derived delineations from 2000 to 2010. And at the bottom is the historic coastal bank position, so that 1990s wetland DEP delineation. At the bottom here, pulled out by the green bars, while the default imagery is the USGS ortho photos from 2013 to 2014 that roughly coincide with the same time period as the LIDAR, I do have the option to turn on other imagery if you wanted to sort of overlay the LIDAR from those intermediate time steps with imagery that closely aligns to the same period. It's not a one-to-one perfect fit, but it gives you a good sense of some context for what you're looking at. So then if you move over into the Legends tab here, if you zoom in to, if you start zooming in closer, this Legends will start populating. And again, it's kind of the rainbow sort of approach. So the oldest being purple is from 1990, blue is from the early 2000s, green from mid-2000s, yellow from late 2000s, and then pink is the most current, 2013, 2014. And then the last thing that popped up in the legend were the coding for the transects. And so those are shown in the sort of light yellow, orange, and red. And the way we binned those was anything that fell within the margin of error, which is largely driven by that 34 feet-ish, 34 feet from the DEP wetlands, that older data set. We put that in this low bin, so the yellow. So as you know, when you explore around here, you'll see a lot of the shoreline does come up in the margin of error, but that's okay because we were interested in that magnitude of change to see where those hot spots came up. And we do have them, and so we coded those as either moderate if they measured at between 35 and 50 feet of erosion, or high, and so anything more than 50 feet of erosion. And then just for orientation here, as I walk through some examples, most of the hot spots that I'll show you are from the Cape Cod and Islands region, an example from the South Shore. But I also wanted to show, if time's permitting, some examples from the North Shore of just another application use of this project. So from the South Shore over in Plymouth, again, sort of the orange is that top of coastal bank, kind of an oblique imagery to get a sense of what the face of this feature looks like. Very high relief, the tool did very well with high relief banks. And then sort of an example of sort of the patchwork, non-uniform pattern of erosion here between primarily the moderate and high. Over on Martha's Vineyard in Chilmark is another example of where the tool performed very well. Again, the higher relief and more sandy sort of composition of these banks, the better the tool performed. And then you can see here is an example of just sort of how episodic this was. It's not like uniformly eroding, which is why we felt like we couldn't present this as a rate. And then just sort of an oblique imagery of this area to get a sense of sort of what the composition and of this landform is. And then still in Martha's Vineyard over in Edgartown, that's very exposed to waves and winds. This is an example where I didn't have that 1990s DP data set to compare to. So the oldest, it's a LIDAR to LIDAR comparison, which gives me a lot more confidence in the measurements that I made because of the higher resolution accuracy. But it's a shorter time frame. So the oldest is from 2005, and the most recent in the pink here is from, I believe this one was from 2014. So, you know, about 10 years of change here, but in that amount of time, this is one of the biggest hotspots we have on the whole coast. So we're looking at upwards of 180 feet of erosion here, and just showing that, you know, between 2005 and 2010, roughly in the same position, somewhere between 2009, 2010, and 2013 is where we see this high erosion sort of manifested here. I did want to give a few last examples of down in Nantucket. Even at this scale, you can see there's a lot of red and orange that pops up, especially down here in the southern extent, or a lot of areas that were missed from the older data sets. So it's going to be, in more cases than not, comparing the higher resolution LIDAR to higher resolution LIDAR. But you'd have to double check by clicking on the individual transects to kind of look at what the data type was. But just as an example of sort of the range of erosion that we're seeing down there, in this case, it does look a little bit more sort of steady retreat as compared to, say, the either the Edgartown or the Chilmark example. This is also an area where we had that low relief of coastal bank, I believe that somebody asked. And, you know, even with a low relief bank, there's still a significant hazard. This image here is from the series of nor'easters that we had last March. And you can see it's definitely an issue, even with a lower relief. Another example of some storm damage on low relief banks, in this case with dune material blown on top. So in the interest of time, I'm going to skip ahead just to show some examples. Great, yeah, so a good range of height here, even just on Nantucket, between that very low relief to the very high relief over in the northeast, the southeast corner of the island. So I did just want to move us along to show another example up on the North Shore of where maybe some of the limitations of the tool are. I mentioned that it does best when you have the high relief in sort of sandy environments. But that said, because there were areas where the older DP data set didn't quite capture all the features, and this is an example here in Nahant of 40 Steps Beach, and also down here at Canoe Beach that was not captured. You can see there's no purple up here, but when you look at the imagery, it's clearly a coastal bank. And so one of the additional uses of this tool is to help resource identification. Some examples of storm damage from last year. And then also Canoe Beach in Nahant is another example of a low relief. So we're looking right in here. It's a low relief coastal bank, but it is certainly eroding. And this is an example of an area where some nourishment was attempted to sort of help with the erosion here. And then finally, just an example on the Upper North Shore in Rockport at Old Garden Beach. An example of the limitation of this tool is you can see they're all in that yellow sort of within the error margin color, which would suggest a low hazard. But we know that the town has recognized an erosion issue here, and so even though the tool didn't quite capture it at the scale that we were doing this desktop analysis, doesn't mean that going out to the site and measuring it and observing it on the ground is still going to be important. So just wrapping up, I touched on this here at the end, just some of the possible applications that we see from this tool is to inform macro-level community planning initiatives. So here in Massachusetts, we have the Municipal Vulnerability Preparedness Program, but there are also a lot of sort of community-by-community coastal vulnerability analysis and helping to inform us here at CZM and over at DEP what those sort of high-level hotspots are. And then I also mentioned the potential to identify resource areas as another tool to help identify resource areas, but certainly would need, ground truthing for any sort of project development or sort of analysis. So that kind of brings us to where do we go from here? Now I mentioned that the toe of the dunes, so the toe of the bank, or the base of the bank, was a proof of concept, and that could be a low-hanging fruit for me to explore next in terms of at least within the LIDAR data sets, sort of trying to apply the same methodology to the toe to see if that is helping explain some of the erosion trends that we're seeing. And then we talked about possibly exploring developing a vulnerability index, and what I have shown here are some of the possible avenues to investigate in terms of, how and why are these landforms vulnerable either to wave climate, say dry beach width, coastal bank height, the level of vegetation, or even present type of vegetation possibly. So these are the kinds of conversations that we are looking to tee up next, I guess. And so with that, thank you so much, and I'm happy to answer any questions that might have come in. So thank you.
Audra, this is Julia. I'm also noticing that Lisa Rhodes is still on the line. Lisa, was there anything that you wanted to add to the discussion? Lisa's our project manager from DEP.
Hi, can you hear me?
Yes. Yes.
Oh, good. Hi, everyone. I'm Lisa Rhodes from MassDEP, and I was one of the key people from DEP who worked on this project, along with Weldon Langley and Michael McHugh. And we're really pleased at the outcome of this project because MassDEP has had a lot of instances of coastal erosion in recent years, and we felt that this tool would allow many different stakeholders to, better understand, where a lot of coastal erosion is happening, and it would help with planning future development. So it's a good tool for homeowners, for realtors, for towns and others that are, planning development near the shoreline. And that was one of the key, it's not a regulatory tool for us right now, and I don't know if it ever will be, but it's an excellent planning tool for many, many reasons. So we're really pleased with the effort that was, put in by Margot and Julia and the others at CZM. That's pretty much it.
Thank you, Lisa.
And someone was asking to see that last slide again, which it looks like you threw that back up. So thank you for that. And then they're asking to post the website. I'm not sure if that's the link to the map, I think, is what they're referring to there. And
yeah,
I can make sure that URL is available when I send out the slides and post that to NUIPIC's website, where all of our webinars will be uploaded online. If you want to get back to that, I think that's what you're trying to do now.
Yeah, it's a really long URL, so I think sharing it the way you just proposed is probably better. I'll just leave it on the vulnerability index slides for now.
So yeah, I'll make sure I send that out to all the registrants. And then another question, was there any associated analysis on structures or roads or other infrastructure?
So this effort was the first step to get a handle on the magnitude of loss of our coastal banks across our 5 coastal regions. And, everything that's thrown out here in the chat box in terms of the relationship of the eroding coastal banks to roads, infrastructure, and how it interacts with the mean high water shoreline are all next steps for us.
And this kind of also falls into next steps, perhaps. And how do you see this tool and the CZM shoreline change study working together?
Right. So we are continuing our long-term shoreline change study with the U.S. Geological Survey down in Woods Hole. We will have an updated mean high water position released in another couple of years, and we'll be able to pull that into the coastal bank erosion hazard mapping effort.
So again, if you have any questions, you can type that into the chat or unmute your line and ask it directly. And I will say that we have several comments thanking Margot for your presentation, and I'll just echo that while we pause for a couple more minutes if there are questions.
If other folks have examples of where contributing factors to coastal bank erosion have been measured remotely on a broad scale, we'd definitely be interested in learning more from folks on the call as well.
Okay, well, Margot, maybe you can put your final slide with your contact information one more time. And that way, if people do want to reach out directly, they can see how to reach you. And I want to, again, extend a huge thank you to both you and Julia and the team that's been working on this for presenting today. And thank all the participants for tuning in. You will have the opportunity as you leave to provide your feedback, which I encourage you to do. And as I mentioned at the start, this is being recorded and I will upload our website. And anyone who's registered today, I'll be sure to send that out so that you know when that's available online and you can share that with others. And I'm going to pause for 1 second because I see a couple of questions that just came in as I'm talking, so I want to make sure we can address those here. So things, the east coast of Nantucket shows minimal change in the shoreline change tool and high change using this tool, so that's interesting. And then another comment, thank you, would love to learn more about the automated approach for delineating crest of the bank, and can we see the methods report? So maybe that's something that you can follow up on. Or maybe you want to briefly address the crest of bank delineation.
Well, I mean, I think this tool, sort of that comment in itself is a good reason why we kind of felt this was a need to fill, because in lieu of it, the shoreline change was being used for features that really aren't captured by shoreline change. So thank you for that comment. That's definitely one of the reasons why we wanted to communicate that these are different parts of the system, but they're, one with these tools that we put out is being able to communicate what the purpose or limitations, appropriate use of these are when we talk about these different components of the coastal system.
Great. So thank you all again, Margot, Julia, and everyone who tuned in today. And our webinar series will take a break for summer, but look for more again this fall. And you can find all of these recorded online on the NUIPIC website. You can reach out to me if you have any questions. Again, that's Audra Martin at NUIPIC. So thank you so much, and the webinar is now ending.